Okay, section 2 is looking at pendulums. So an example of a pendulum would be a grandfather clock. So the grandfather clock in the hallway operates with a pendulum. It's a beautiful clock, but is running a little slow. You need to make an adjustment. List anything you could change to correct the problem. So think about how, I don't know if you're even familiar with how you work a grandfather clock, but think about different ways you could change that pendulum. And how do you think it would change? Because each pendulum swing is supposed to be a second, right? So how could you change that? So let's look at that. Amplitude is the maximum displacement from equilibrium. We use meters, and the period is a big T again for the time for one complete cycle, and we use seconds. Frequency is the number of cycles in a unit of time, and we use hertz. Seconds to the -1, or cycles per second, but it would be hertz. And so the relationship between period and frequency is their inverse of each other. As the period goes up, the frequency would go down, and vice versa. And here's a little equation. When it talks about amplitude, displacement from equilibrium, for a pendulum, equilibrium is right in the center, and so the displacement would be how far it's moving from the direct line.
Equilibrium point. Amplitude is measured in radians or meters. Period is the time it takes to execute a complete cycle of motion. Period is measured in seconds. Frequency is the number of cycles or vibrations per unit of time. Frequency is commonly measured in hertz or cycles per second. This pendulum has made 3 complete cycles in a unit of time, so its frequency is 3.
Okay. So as an example of the pendulum. So for simple pendulums, we use small angles so that you're not taking it from the equilibrium very far. The period depends only on the length and the value for g, acceleration due to gravity. So the mass of this bob down here does not affect the period. All masses accelerate at the same rate. So here is the equation for the period of a simple pendulum in harmonic motion. Where big T, remember, is period, equals 2 pi times the square root of L, which is the length of the pendulum, divided by gravity. So here it would be 9.81 meters per second squared. For a spring, the greater the spring constant would give you shorter periods. So stiffer springs provide greater force. It takes more force to displace that mass, and therefore greater accelerations because it's going to pull it back to equilibrium faster. The greater the masses, the longer the period. Large masses accelerate more slowly. So it is related to mass and K. So the period of a spring is equal to 2 pi times the square root of m over K. Now sometimes you'll see TP and TS because it's specifying period or spring. So here is a sample problem. We're looking at a pendulum. What is the period of a pendulum that's 3.98 meters long? What's our equation for our pendulum? The period is equal to 2 pi times the square root of L over G. So all we have to do is T is equal to 2 pi. The length, we need it in meters, and it already is, so we have 3.98 meters over 9.81 meters per second squared. Meters cancel out, and you should get, let's see what the answer, you get 4 seconds and 2 seconds. Okay, now the difference on that second question, when it asks about the period and frequency, remember our equation is T is equal to 1 over F. So if we knew our period was 2 seconds, and that second one with a 99.4 centimeter long period, we could have, well, we could do F is equal to 1 over T also, or equal to 1 over 2 seconds, which is equal to half a second. Oh, not half a second. Sorry. Hertz. Okay, so here's one more example you can do. This time it gives you a back and forth once every 1 second. So that's going to be your period, and you're going to find L. Use that same equation. You should get 0.25 meters. Try that one on your own. And last problem, what is the free fall acceleration? So you're looking for G. You have a 6-meter long pendulum, that would be L. 100 cycles in 492 seconds. You're going to have to find the time of one cycle. So you're going to divide by 100, which would be 4.92. So you should get 9.79. Try that one. You're using that same equation. T equals 2 pi times the square root of L over G. You're solving for G. Okay, your equation for a spring constant, remember, is T equals 2 pi over K over M. I take that back. I did that backwards. M over K, right? M over K. Okay, so you're trying to find the spring constant, so find K. You should get 9.9 Newton meters. So now how can you make an adjustment to the time? For a pendulum, all you can change is the length. By changing the mass, it doesn't change anything.